Welcome. My name is Anton Hlöðversson, and welcome to my master's thesis defense in language technology. The subject is spoken language understanding for Icelandic reservation system and translated corpus. For the next 20-25 minutes or so, I will give a short description of language technology, its applications such as spoken dialogue systems and spoken language understanding. I will go over how spoken language understanding can be used in an airline reservation system, followed by an introduction to the ATIS corpus. After, I will state my research questions and how I roadmap my entire project. I will follow it by talking about the byproducts of my research, the text annotation tool, and the slot filling and intent determination models. I will introduce the evaluation metrics that I use to measure the performance of my models, and finally, I will wrap it up by bringing up some discussion points and my conclusion. Language technology is an interdisciplinary field of research and development that spans multiple fields such as computer science, linguistics, artificial intelligence, psychology, and etc. It's the research field of how computers work with human language in both spoken and written form. For the last decades, we have seen a rapid innovation in this field, and the biggest companies out there, such as Google, Amazon, and Apple, are all language technology companies, offering tools such as machine translation, web search, and for our smartphones, auto-completion, and even personal assistants such as Siri, Alexa, Google Home, and there's even an Icelandic one called Embla. These personal assistants are known in our field as spoken dialogue systems. And spoken dialogue systems are computer systems that handle both speech input and output. What most of these systems have in common are they try to respond in as natural way as possible and are able to keep track of a state of a conversation. And the 5 main components of a spoken dialogue system is the automatic speech recognition that converts the audio waves signals into text, the natural language understanding or spoken language understanding, then tries to capture the meaning of an utterance. The dialogue management system performs can perform requested actions, keep track of the conversation, and decide what to respond to the system user. The natural language generation system takes the response and converts it into text that appears to humans as natural text. And the speech synthesizer or text-to-speech generates speech from that text. So spoken language understanding is the main topic of this research, so I will take a closer look at it. As I mentioned, spoken language understanding has the responsibility to try to understand the utterance from the system user. It does this by attempting to create structured data representing the utterance, which captures what action to perform with what set of values. And these tasks are called intent determination, to understand the main intention of the user, in other words, what action to perform, and slot filling, to extract essential values within the utterance. In an airline reservation system, intents would correspond to a list of actions available within the system, such as to retrieve a list of available flights, destinations, available airlines, or even to retrieve information about price. The slots, on the other hand, would correspond to essential information, such as the departure location, destination, the date and time. As seen in the given example, we're able to determine that the user's intent is to find a flight, and the slot values are Keflavik and London for his departure and destination, respectively. From the 1990 to 1994, an American non-profit research institute, the SRI International, worked on the ATIS project on spoken language understanding. A byproduct of that research was the ATIS corpus, consisting of 5,871 samples, and each sample consisting of speech utterance, transcription, and annotation. Besides that, a related database was created containing mock data for testing purpose for the dialogue management system. In the year 2016, Microsoft publicly published the ATIS text corpus in their cognitive toolkit, a collection of tools and data to use deep learning for researchers and developers. Since then, this text corpus has been used as a benchmark dataset for the spoken language understanding for airline reservation system. Currently, there is no comparable corpus available for Icelandic yet. As so, with this limited amount of data, time, and resource, would I be able to create a baseline spoken language understanding for Icelandic Airline Reservation System by simply translating the ATIS text corpus directly to Icelandic? And if so, how well would it perform? And those are my kind of research questions. And going into the research, I broke the project into 4 milestones. The first milestone would be to create a tool that could help me to translate by keeping track of my progress of my translations, ensure data quality, and to use an available machine translation to help me to speed up the process. The second milestone would be actually to translate the ATIS corpus, not only to translate it, but also to export data from my database to more usable format. And lastly, to ensure data quality even further by checking for any typos, for example. The third milestone would be to create a baseline spoken language understanding model, focus on using naive approaches to allow easily further improvements, and to use only my translated corpus and no external resources. Finally, the last milestone would be to choose and apply a commonly used evaluation metrics on my models. For my translation tool, I created a web application that is hosted online. This allowed me to work on it anywhere at any time. And I designed this tool to be able to possibly support other languages than only Icelandic. And I used Google Cloud Services to use Google Translate to help by suggesting a translation. And finally, to help me to re-annotate the data as needed. A fun fact, this tool is currently being used to translate ATIS text corpus to Spanish. Next, I will introduce 2 separate models that were made to solve each of the tasks of the spoken language understanding, a slot filling model and a model for the intent determination. Slot filling is a tagging task, which means to label each word token to an utterance with a slot tag. These slot tags are of the IOB format, short for inside, outside, and beginning of a slot value. The BOS and the EOS in the example shown are word tokens that stand for beginning of a sentence and end of sentence, respectively. N-grams are statistical language models that are commonly used for these tagging tasks. And an N-gram model are created by taking the whole training set and break it up into pairs of word tokens and the corresponding slot tags. A unigram only pairs a slot tag to one word token, and when used for tagging, the most frequent instance of the pair is used as reference. In the example shown, let us say the word token Seattle only appears only 3 times throughout the whole training set, and the most frequent associated slot tag is this B from located city name. We would then assign the slot tag to any Seattle word token in an unseen sample. This applies also for bigrams, but instead of only pairing it with a corresponding word token, we also add the preceding word token to the tuple. The idea is if we're able to capture the surrounding context, the model should perform better. We did this also for our trigram model, but instead of only including the preceding word token, we included the following word token as well. And now that we have created these 3 different N-gram language models to help us to classify which slot tag to use for each word token, we want to classify the whole utterance as a whole to an intent class. And intent determination is a classification task where we do not look at each word token, but the whole utterance as whole. In our data set, we have 26 different intent classes. We're working with an unbalanced data set where one class is more dominant than the others. The flight intent makes up about 73% of all the samples in our training set. And for this task, we chose to use the feed-forward neural network, the simplest form of an artificial neural network. A feed-forward neural network consists of 3 main layers: an input layer where an input symbol goes in, an output layer that spits out the probability for each class. The hidden layer in between the input and the output layer performs a nonlinear transformation of the input entering the network. But there's one catch. Neural networks can only process input values in a numerical form. So how do we convert a string of text or word tokens into numerical representation for our input? Word embedding is when words or phrases form a vocabulary are mapped into vectors of real numbers. For our network, we use the bag of words or word embedding created from the training set. We can imagine that each of our sample is a dictionary where each instance correlates to one word in a vocabulary. The word embedding is a vector consisting of only zeros except for the indices of the word that appears in our sample. These indices values get the value of 1. In other words, these word embeddings are one-hot encoded vectors of the length of the vocabulary consisting of only ones and zeros, zeros for each word that did not appear in the sample and ones for words that appeared in our sample and for our input sample. And now that we know how to represent our sample as numerical vectors, we can take a closer look at the whole architecture of our neural network. The number of nodes in the input layer correspond to the length of our word embedding. For our hidden layer, we have 2 fully connected layers of size 64 and 32 respectively. And where we have 26 intent classes, we have 26 nodes in our output layer. Even though I do not indicate it on the figure, but I included dropout between each layer for regularization purpose. Now that we have the SLU model ready, SLU models ready, we need a way to evaluate the performance. We chose to represent the performance of our model by using an F1 score. F1 score is one of the common measures to rate how successfully a classifier is. It's the harmonic mean of 2 metrics, namely the precision and recall, that corresponds to a ratio of type 1 and type 2 errors, respectively, for each of the classes. We are looking at we are looking for a balanced measure between precision and recall. And in general, we prefer classifiers with high precision and recall scores. But however, there is a trade-off between precision and recall. When tuning the classifier, improving the precision score might result in lowering the recall score and vice versa. But unlike binary classification, where there's only 2 classes, a multi-class classification generates an F1 score for each class separately. So we need a way to represent the whole value, like a single value for all of those F1 scores. That is where F1 averages comes to play. One approach would be just simply taking the average for all of the per class F1 scores. This would be referred as the macro averaging. But by doing so, we're giving each per class F1 score the same contribution to the final score. But this is a problematic to our data set as it is unbalanced, uneven numbers in each class. So this method would not represent the performance of our model at all. There are 2 ways that we can solve this. We can either calculate the F1 score over all the true positive, false positives, and false negatives for a whole data set with no regards in what class it came from. Calculate the precision and recall accordingly, and then to calculate the overall F1 score. This is what is called microaveraging. The other approach is to use the number of samples in each class to weight upon each per class F1 score, and then take the average over all the number of samples, the overall number of samples. And this is what is called a weighted average. Here we see the F1 score using the 3 different averaging methods. Even though macro averaging does not belong here, I included it for demonstrative purpose. On the other hand, we can see that we get quite similar results using the 2 other latter approaches. Both of them are okay to use, but just keep in mind that micro averaging does not consider from what class the true positive came from, and the weighted average is considering the proportion for each class in the dataset. From the results, we can see that bigram model give us the highest score, and higher is better. And here are the results for our intent determination models. The same approach was applied. The reason why you see 2 mentioned models is because after a good feedback from the committee, I decided to evaluate the model by removing the second hidden layer in my network. I had earlier assumed that 2 layers would generalize and perform better than 1. But in our case, it seems that we get better scores by keeping our model to only one hidden layer. And looking back at my initial research question, I would say our research was a success. We were able to create a baseline SLU models using a translated corpus, and it performed better than I had expected using these naive approaches. Nevertheless, there still leaves room for improvements. Firstly, by just including some external resources. We could, for example, just by data pre-processing by using lematizer. By lemmatizing each word, this would drastically reduce the size of the vocabulary. We could try different oversampling approaches to kind of even the data classes out. So, and one thing about the data set, it is already predefined split between the training and the test set. But it would be great to just evaluate this in a like a tenfold cross validation, and just to try and have a way to ensure that data appears like a similar data appears in the training set and the test set. And if an airline reservation airline company such as Icelandair would take this model, they could use this. But just by replacing the destination and locations based on their set of their service, and even trimming out unused clauses like asking about what meals are on board or some transportation. By removing these smaller classes, you would theoretically get a better performance. I want to thank you for this time. I want to thank my supervisor for like helping me out throughout the research, and I want to thank the committee for a valuable feedback. And I want to thank the language technology community here in Iceland for a great work, and I want to thank my friends to show up to this presentation. So now we are opening now it's open for questions. So maybe Jon, you can I don't know.
You can unspotify him now. Jon.
Yes, unspotify.
Unspotify, yes.
Or
all my
Spotify,
playlists. Yes.
Unspotlight.
Unspotlight.
So thank you very much, Egill. Well done. I think we just open the floor for question. I suggest that you just say something in the chat, and I'll use that as a to say I want to ask.
Yes. So if you have a question, type it in the question, and Jon will ask the question.
Yes, or you can ask it yourself. I'll give you the floor if you want to.
Yeah, just one at a time.
So we will. So Anna has a question.
Yes.
Please, Anna, you start. Thank you.
I hope you can hear me. Good morning.
Good morning.
Egill, I was just curious, did you have any way to deal with unseen words? Like if a user uses your tool and uses any word that is, for example, not in your vocabulary. I saw your vocabulary had a length of 1,300 something, I believe, for the neural network. Is there any way you thought about how to deal with unseen words?
Yes, so let's go back to the slot filling task when there was some word tokens in the test set that did not appear in the training set. My approach was to use the default value of the outside of vocabulary when it didn't recognize the word token. It just had to fall back to a default value.
Well, thank you.
I have a question.
Yes, good. Thank you. Thank you, Anna.
I was wondering, did you consider using pre-trained word embeddings, for example, for the slot filling task?
Yes, as I mentioned in the discussion, it would have probably improved the model or the results of the model by using a pre-trained word embeddings from a larger corpus that represent the language better. Yes, but my focus on this research was to not use any external resources. I just wanted to focus on creating a baseline using only this corpus alone.
Thank you. Haukur, do you want to follow up or?
No. The baseline answer was the one I was.
That was the focus, and yeah, there's plenty of things you can do, and please ask about them. It's interesting. It's a very interesting continuation of the project to include. Yeah. Benedict, you have a question. Do you want me to read it up, or shall I read it up?
Hi, Egill. Can you hear me?
Yes, I can hear you.
Yes, very good. A nice presentation, the parts I caught. I didn't catch it, I had to stand up, but how did you translate the dataset you were using?
I created a tool that helped me to speed up the process. I had put all the dataset into a database. Then by going by one, I used a machine translation through Google service that would suggest a translation. I would correct it, and then use then re-annotate the slot tags as needed.
Right. So I think it's been a while since I've used Google to translate from English into Icelandic. But is it still like, how reliable do you think this translation is?
I was not able to, like I would say, in most cases, almost all of them, I had to manually correct some of the translations, and some of them I had to totally throw out and just kind of translate it manually. And
okay. Sorry, out of interest, did you keep the original translations? Can we see the edits that you made in the?
No, I did not keep the translation from the machine from Google. I just had it as a suggestion, and then I would just overwrite it, fix it, and then. But it would be no problem going just with a script through all the original data set and just give out the machine translation.
So we could evaluate Google there if we
yes, you could do that. Yeah. or make even a or a model that could correct a Google translation to my translation.
Let me just say, about this part of the project, that this was a real sort of it just shows that, in a good master thesis, you have to overcome a lot of practical difficulties. So from an engineering point of view, this was a real heavy task that Egill managed to do that just with this thing. So it was quite a good resource that we have from the project.
And this tool is publicly available on my GitHub account. So feel free to run it up, get some feedback, or participate by improving on it. There are some open issues that needs improvements, but I was able to complete my task with the version which is available. And I mentioned Lucas, my friend. He is creating a Spanish version of it, and he has almost done with it.
So we could do a multilingual version of this project.
Yeah, or even use it in other scene to create not only for spoken language understanding, but more like for our own machine translation.
Okay, thank you, Benedict, for your question. Hrafn, you are next.
Yes, can you hear me?
Yes, we can hear you.
Okay. So you had 3 types of different language models that you evaluated for the slot filling.
Yes.
I think you showed that the bigram one was actually the one that got the highest F1 score.
Yes.
Very often, when you extend the history, like if you go in this case up to trigrams, you get better scores.
Yes.
In your case, that's not the case. So do you have any explanation for it?
No, I did not go into depth into looking at which samples were getting the, like what is the nature of those mistakes. I did not go that deep.
Okay.
Okay.
Any further questions, Jon?
No, I mean,
I had I had one, right?
yeah, there are more questions. So we move on. Hannes, please take the floor.
Yeah, the presentation was really great. I really enjoyed it.
Thank you.
One thing maybe you can say a little bit more about is so the translations from the English sentences. So that's a really important step, and it's nice to have this tool to help you do it. But what is your sense for how well the data set itself captures the manner of speaking in Icelandic? So if you actually think about the interactions with between Icelanders and such systems, would you expect that some sentences would come up that would not be covered by the English data set?
There were some like for each sample, I had to translate it to Icelandic, so it could kind of represent Icelandic spoken language. So it was sometimes difficult to do that, but as these are more like short utterances, more precise, it was really seldom that I had a problem to kind of create
rephrase.
Yeah, or to like a better rephrase. But a note taken is that this translation is kind of biased towards me, so it doesn't represent completely like the whole Icelandic community. So I would suggest, for example, if Icelandair would take this project even further, they should start collecting some actually real data from other people than just So I would say, but I had that in mind that I did not rephrase all of the sentence, which are similar, to all exactly the same. So I kept that in mind to have a little bit like fluctuation on how I rephrased the samples.
Mm-hmm. Thanks.
Thank you, Hannes. We'll move on. We have a few questions more. So Luke, please.
Yeah. Hey, yeah, such a cool project. And I just wanted to ask about the post-editing translation tools, because it looks like super user-friendly, and you were saying that it's being used for Spanish now.
Mm-hmm.
Did you look into outsourcing translation at all? Because this is so big for English. Is that just not feasible?
That would be great, but outsourcing it, firstly, you have to focus on getting, especially for this task, to translate it to Icelandic, I would have to hire some, like outsource it to Icelandic translators. And it's firstly, I did not have the financial resources to support that, nor and I saw that I was able to kind of manage it on myself, but to outsource this to any other languages, like I have it as an open source project, so I just hope that by even bringing this to some conference or something, some other other environments to kind of advertise this. It's more like to get like more languages. I have asked a couple other friends that have other kind of native languages like Greek or I don't know, it's called Farsi or something, to translate it. They will be, they are interested to help, but like I say, it would be a great thing if this could be a large, become some like a larger, like a community project.
Yeah, cool. Cheers.
Thank you, Luke. Haukur, Páll, you have another question?
Sorry, were you offering me to ask a question? My internet became unstable.
Yes, you are.
Yeah,
you're on.
thank you. So one more question about so did you try attaching an ASR to your system, and how would you expect that to work, like for a more end-to-end solution?
To do an end-to-end solution, I would have to kind of implement all of the 5 components to kind of to create this the spoken dialogue system, and I did not apply any other components. There are automatic speech recognition being developed. There are speech the speech synthesizers being generated created, and we are just waiting that they become more robust. Then I would expect that it could be easily all put together, and this is just a subject for another research or another topic.
Thank you, Haukur. Sigurjón just says congratulations on your project. Really interesting stuff and great presentation. I don't expect he has a question.
Okay, then I just thank you.
So I think the only other question we have is Anna again. If you please
Right.
make it quick.
I forgot. Congratulations on the project. Should have said that first. My bad.
No problem. Thank you.
You managed. You mentioned Iceland Air. Is this project a cooperation with them?
Yeah, so they were the sole sponsor of this research.
Cool. So did you come up with the topic yourself and approach them with it, or was it them
partially?
Initially?
They just had the general topic. It went through Hrafn and Jón, I expect, and the committee here in the Reykjavík University. They suggested to Iceland Air to look further into this kind of spoken dialogue systems in their booking system, and they had accepted, and they gave funding for that project. But then to decide to narrow down to specify what I would be doing, that is my topic that I chose by focusing on the spoken language understanding models. Because and the reason why I chose that instead of all of the components is that some of the components are still missing for Icelandic, and some of the topics is not for me to actually to apply, like the dialogue management system. That would be something that done by the kind of the back end of Iceland Air specific. But so I saw the only kind of available topic that I could work with, focus more on was the spoken language understanding.
Nice, thank you.
Thank you.
So thank you, everybody. We might have one quick question if you want to, but there's no one asking for the floor. So if
then I just say just thank you for attending.
Thank you, everybody, for coming, and I suggest we give Egill a round of applause.
Like I see that Hannes has this applause emoji.
So let me just say also that apart from the feeling of applause, which is a bit pathetic online, everything else seems to be working really well. So I really like this format, and thank you for all your comments in the text as well. So thank you for coming, and I will now just ask you all to leave. So we will have a discussion with the committee and Egill. So thank you, everybody, for coming.